Earth orbit is filling up at an alarming rate. Nearly 6,000 satellites are now circling our planet. About half of them are dead and circle the Earth as space junk. Millions of pieces of debris are also hurtling alongside them in orbit. And the trend is increasing. Space junk can have devastating consequences. It threatens not only manned space travel, but also our satellite-dependent digital world.
Space junk is and always has been a major topic. But let's be honest, nobody really knows exactly what's going on. How dangerous is space junk actually? Under the current conditions, can we even continue to travel into space? Are our astronauts safe at all up there in the space station? One example, a particle measuring just 1 millimeter in diameter recently smashed into the pane of a module of the space station and damaged it. And I can assure you that had it been 1 centimeter in diameter, it would have caused a catastrophe.
The International Space Station circles the Earth at an altitude of about 400 kilometers. Its speed, 28,000 kilometers per hour. The orbit of the ISS is continuously monitored from the Earth, partly to avoid a collision with debris. But the object that damaged the pane of the observation cupola in 2016 was much too small to have been detected. Perhaps the fragment was just a splinter of metal or a particle of paint. A 1 centimeter particle, on the other hand, could have been life-threatening for the crew, or at least caused serious damage to the space station.
Space junk in Earth orbit is dangerous for people on the International Space Station simply because it's moving at very high speed, 10 kilometers per second. So here's the thing. When something is moving at very high speed, even if it's very lightweight, its so-called kinetic energy is very high. The kinetic energy then becomes as high as the energy of multiple kilograms or even tons of explosives, and so you can understand how extremely dangerous it is just to collide with some little screw flying around out there.
In June 2011, an unidentified fragment crosses the path of the ISS. The object is detected too late to execute an evasive maneuver. The space station is evacuated. For safety, the crew boards the 2 Soyuz capsules. The object passes the space station at a distance of just 250 meters.
Normally, we try to detect the approach of such space junk well in advance. Sometimes, however, objects appear suddenly because they remain unseen for much too long. Examples of such objects include ones with very eccentric orbits, which cannot be measured very often, where the opportunity to measure them is very limited.
About twice a year, the ISS executes evasive maneuvers to avoid large debris or dead satellites. An evacuation into the Soyuz capsules is a genuine emergency. And even then, the crew members need enough time. The space station is at continuous risk of being hit, even though the debris in such low Earth orbits does not stay in space forever.
Service life in Earth orbit primarily depends not on the size of the object, but rather on its altitude. When I'm in the low range and low Earth orbit, then I still have a residual amount of Earth's atmosphere there that has a braking effect on my objects. In other words, atmospheric drag causes them to lose orbital energy and fall back to Earth as a result. So, as an order of magnitude, we say that an object placed at the altitude of the International Space Station, about 400 kilometers, will remain in orbit for 1 year. After that, it has left orbit. At 600, 650 kilometers, there you have to expect a service life of about 25 years.
The available space around our planet is gradually becoming scarce. It is estimated that there are 35,000 objects in Earth orbit, which are larger than 10 centimeters and no longer have a function. They represent the most dangerous segment of space junk. Observers on Earth know the orbital data concerning about 20,000 of those objects, but the further they are from the Earth, the harder they are to locate. These objects are monitored primarily by the U.S. Space Surveillance System, a network of telescopes and radar systems which continuously monitors Earth orbit. It is under the control of the U.S. Department of Defense. Established already in the early 1960s, that surveillance system is now part of the newly created United States Space Force, the space arm of the U.S. Armed Forces.
In the past, the Americans always provided the data to us very reliably. We are currently in the process of developing the relevant competences in Europe too. It's an SST program, or in other words, a tracking program. It's being financed chiefly by the European Union, and the ESA is also involved, of course, to also provide access to all the information collected. I think all this data should be made public. It's not secret data. We say it, but then we don't say where it's flying. Well, you can see that for yourself.
Of course, the governments of all countries want to know what objects are flying out there in space. That healthy curiosity originated during the Cold War. Intercontinental missiles travel a large share of their trajectory in space.
They were detected with radar systems, systems that were originally designed to detect intercontinental missiles. From those systems, the first orbital data catalogs were then developed. And then for very high objects for geostationary Earth orbit, those objects out there were just detecting using telescopes. And it's actually true that there are certain objects whose orbital data are not published. But it's also only fair to say that most of those objects are in very low orbits. That means when they fall out of orbit, they disappear. And some of those objects also disappear from Earth orbit very quickly. That means we have to assume that those objects undergo controlled re-entry, for example.
Orbital data from Earth orbit are primarily recorded and published by the U.S. military, except for its own secret objects. But even the U.S. military is still unable to monitor dangerous, centimeter-sized debris.
In space, close to Earth, all particles have the same speed, roughly between 7 and 8 kilometers per second. That corresponds to 25,000 to 28,000 kilometers per hour. The question is, how much force does that represent on impact? I've brought along an example of such an impact site for you here. This is what it looks like. A 1-centimeter ball has been fired into a massive block of aluminum right here. It's pretty heavy. Now, the question is, how can the International Space Station protect itself from something like that? An aluminum block like this is of no use at all. And the answer is, you have to use a trick, the so-called Whipple shield. The Whipple shield provides just enough protection against such impacts. For larger or faster particles, however, even the Whipple shield won't help.
The astronomer Fred Whipple invented the shield, which is designed to protect manned and unmanned spacecraft against debris and micrometeors. All endangered areas of the space station are fitted with such shields. A Whipple shield normally comprises 3 layers, whereby the first layer is used to break up and disperse the penetrating object. This distributes the energy among many fragments, which are then absorbed by the remaining layers. The question is not whether the space station will be hit, but rather where and how large the object is.
There's a gap in our knowledge of objects, ones we cannot see and whose orbit we cannot track. There are developments aimed at also monitoring such small objects, but there are huge technical hurdles to overcome. For one thing, we have to be able to detect these small objects in the first place. That means a system must be powerful enough to detect a small object in order to track its orbit. And I am receiving more and more measurements. At the moment, I have roughly 20,000 objects in the catalog. When I go into the centimeter population, then I suddenly have 100,000 objects whose orbits I have to measure.
And then, when the fragments in the millimeter range are added, the number of debris particles rapidly grows to many millions. In February 2009, two satellites collided in orbit for the very first time. The defunct Russian Cosmos 2251 struck an Iridium communications satellite, a worst-case accident.
At first, the resulting debris continues flying more or less along the same orbit because it has such a high orbital velocity. The additional speed then imparted by such fragmentation causes the cloud of debris to expand over the course of time. This means that within a relatively short period of time, the cloud of debris is no longer compact. When I look again weeks or months later, then the orbits have begun to move apart from one another. That's called orbital drift, which means that the orbits that were once at the same orbital level continue drifting apart until after a few months or years, this debris is ultimately distributed throughout Earth's orbit in that orbital region and at that altitude.
More than 3,000 detectable objects have been set free by the collision and are now careening around the globe. A tremendous danger for other satellites.
The available space that Earth orbit provides is actually smaller than it appears to be because only certain orbits are of particular interest. This is the so-called geostationary orbit, 36,000 kilometers above the surface of the Earth. When you place a satellite there, then it remains at that fixed point. The Earth then rotates exactly together with the satellite, and so you have a satellite that always stays over the same point. And it's particularly easy for you to communicate with that satellite. So that orbit is in especially high demand and should not be cluttered up with debris. And then there are the orbits in which the International Space Station is located several hundred kilometers above the Earth. They're also of special interest because there's not really all that much room up there, considering the fact that every small screw represents a serious risk. So it seems like there's plenty of room, but in reality, there's not so much.
Orbits around the Earth are getting crowded. The near-miss collision of the U.S. space telescope Fermi and the defunct Soviet spy satellite Cosmos 1805 is further proof. Only by changing its orbit did Fermi manage to escape destruction by a Cold War relic. The old Soviet reconnaissance satellite missed the telescope by barely 9 kilometers. The rescue maneuver used the rocket thrusters that will also propel the telescope into the atmosphere to burn up at the end of its service life.
We also have several thousand out-of-service satellites flying around the Earth. And that's, of course, an issue when we consider space as infrastructure. And infrastructure all cluttered up with rubbish is not a good one.
Without communication satellites, Earth observation and weather satellites, or navigation satellites, the digitized world as we know it today would no longer work. We have become completely dependent on data streams from space, even if we're not always aware of it in everyday life. Nowadays, satellites enable telephone conversations, television, and the internet. So every time you use your smartphone also involves aerospace applications. Today, the orbits around the Earth are an important and sensitive economic factor, one that every country tries to safeguard for itself. The new German space radar Gestra, for example, will also provide for greater security in space.
A national system enables a country's own independent assessment capability. That means that we can use it independently from other nations to determine what's out there in space and whether danger threatens our satellites.
This state-of-the-art radar system comprises 256 separately controlled transmitters and receivers and can monitor objects in low Earth orbit around the clock. In that way, Gestra provides continuously up-to-date situational awareness in space. But the acquired data are also added to the European Orbital Data Catalog.
The system is designed to monitor low Earth orbit. That means we can detect objects orbited at an altitude of between 300 kilometers and 3,000 kilometers. And the system itself is a so-called phased array radar. Phased array means that the direction in which we look need not be determined by the mechanical rotation of an antenna, but rather can be set up purely electronically. This enables us to search a large area in space in a very, very short period of time, laying out a search grid with which we can then detect objects that fly through that search grid, and then we can track their orbit.
The radar is operated from the Space Situational Awareness Center of the German Armed Forces. And the system will also make it possible to achieve gradual independence from the U.S.-American Orbital Data Catalog. Every rocket launch leaves space junk in orbit, and the limited service life of satellites only makes matters worse. Depending on the altitude of their orbit, those defunct satellites then continue to drift in space for a very long time. The extreme conditions that prevail there cause materials to fatigue very rapidly. And as a result, many objects break up on their own into smaller fragments, which are in turn distributed around the globe where they endanger manned and unmanned spacecraft.
So, how was it back then with the space shuttle? Well, first of all, the space shuttle was much smaller than the space station, and missions only lasted 1 or 2 weeks. And that's why, according to NASA, only 1 out of 1,000 missions were at risk. And that, in turn, was the reason why the shuttle had no protection. NASA told us astronauts that if an object hits the shuttle, you'll just have to put on a pressure suit and return to Earth immediately. Of course, the shuttle did suffer impacts from time to time, but they were only very small particles and therefore caused only relatively minor damage.
The space shuttle was designed to be NASA's workhorse. The 2 space shuttles that Americans lost cost the lives of 14 astronauts. Though neither of those accidents was caused by space junk, the space shuttles were not invulnerable to debris hurtling through space. There were numerous near-miss collisions with objects in space, like this piece of junk that flew past the tail of the Atlantis on mission STS-43. Nor were small impacts rare. Hits like these in the flight deck panes of the space shuttle could have been fatal had the debris been a little larger. Extensive damage was documented during every routine inspection upon return from space, especially after the missions involving the Hubble Space Telescope, which circles the Earth at an altitude of about 550 kilometers. Numerous impacts were identified. The Hubble telescope was transported into space in the cargo bay of the Space Shuttle Discovery and placed in orbit. 5 more shuttle flights then returned to the telescope on repair and maintenance missions. And technicians regularly found a large number of impacts in the space shuttles upon return to Earth. And then, during a service mission in 2002, one of the solar modules of the Space Telescope was also replaced. The old collector was brought back to Earth, and the scientists found several thousand craters on it caused by space junk, some of which measured several millimeters. Testimony to the serious risk of fast-flying particles orbiting at that altitude.
At 28,000 kilometers per hour, even small fragments can cause damage, of course. The film Gravity provided us with a very impressive depiction of that. This is a genuine risk that can endanger astronauts. It can also endanger the International Space Station. And with that in mind, we must do something to protect against both large and small objects. The issue must be taken seriously, very seriously.
Sonic boom's announcing Discovery's arrival. It's now just 68 miles away from Kennedy Space Center. 27,000 feet.
The double sonic boom announces the return of Discovery after a mission in Earth orbit. NASA's space shuttles completed a total of 135 space flights, and ultimately, It was pure luck that no third accident occurred, caused by a large enough piece of space junk crossing the path of the space shuttle. The internet site stuffin.space offers an amazing view of the Earth. Based on the U.S. Orbital Data Catalog, the American programmer James Yoder creates a three-dimensional map showing all the objects in Earth orbit in real time.
Now let's see just what the space junk situation actually looks like. To do so, I have an app here that displays an animated graphic of scrap for me, debris from an American catalog of space junk. What do we see? We see different colored points. Red indicates active satellites. Blue means broken ones. And these gray points are other debris. First of all, we see that most of the pieces are flying close to the Earth. That's the so-called near-Earth space. Now, when I zoom out a little bit, then we get a better overview and we see that out here we have a string of pearls. Those are the geostationary satellites, and that means the active ones, all in red. But we also see that there's a sort of ring around the geostationary orbit, and that's all the ones that can no longer be controlled properly. So they leave this string of pearls. In addition, we see here a sort of cloud of satellites, which are somewhere in between. Those are the navigation satellites of the Chinese and the Americans, but also the Europeans. And now, what we'll do is, we'll pick out any object at random. So I tap here on one of these points, this one for example, and we see a Cosmos satellite, a Russian satellite, launched in 2016. You can see that here. And here in green, you see its orbit. By the way, this red string of pearls that you see here, those are the brand new Starlink satellites from Elon Musk. He recently sent them into space, and now they're circling the Earth like a string of pearls.
Starlink is a network of small satellites that Elon Musk's aerospace company SpaceX uses to provide high-speed internet from Earth orbit.
Starlink
is Elon Musk's project to build a constellation. His is now the operation with the most proprietary satellites out there. It's really quite amazing. He has accomplished so much here. But Starlink did have two aspects that have to be taken into consideration. The first is that it's a constellation that places many, many satellites out in space, thereby also clearly raising the question of space junk. And the second is that Starlink obviously made them easy to see, and astronomers were not very thrilled about that.
Scientists are worried about their unobstructed view of space. Today's time-lapse recordings of the starry sky are already interrupted time and again by satellite clusters. And the Starlink constellations are clearly visible in the night sky, especially in the deployment phase. The Internet from space will be accessible around the globe, and it will require a huge number of mini-satellites. SpaceX has applied for launch approvals for up to 30,000 Starlink satellites in the next few years. New space. Clearly, the ever-increasing commercialization of space still has some surprises in store for us. The once ridiculed SpaceX idea of landing the first stage of a Falcon rocket autonomously for reuse has already become routine. This does not prevent space junk, however, because the upper stage of Elon Musk's rocket remains in space. It takes multi-stage rockets to reach Earth orbit, and the upper stages that remain in orbit are what actually cause the big problem.
The real question is, how do we measure the risk? How much debris can be created when an object is struck and disintegrates? And the upper stages are particularly significant here due to their large size and weight. Because when a large, heavy object is struck, of course, the impact produces a much higher number of fragments than when a small satellite is hit. So it might be an overstatement to say that there are very, very many upper stages, but the risk inherent in an upper stage like this, when struck by an object, that risk is clearly higher than with a small satellite.
Since the very first rockets were launched into Earth orbit, people have also been leaving their rubbish there. Starting from the 1960s, aerospace activity experiences a boom. In the space race between the two superpowers, the USSR and the USA, an ever-increasing number of ever more powerful rockets are fired into space. And in so doing, they also leave more and more objects in orbit. At the dawn of the aerospace age, however, this is of no concern to anyone yet. The Apollo moon missions alone send several tons of scrap into space. Much of the debris left behind then is still circling our Earth today.
We still find objects from the early phase of space travel in orbit. The Vanguard 1 upper stage and satellite, which were launched in 1958, are still in Earth orbit. That's essentially the oldest space junk to be found.
The remnants of a particularly adventurous plan also originated from that time. The U.S. military wanted to use hundreds of millions of copper needles to create an artificial ionosphere around the Earth. The project, known as West Ford, failed. The clusters of copper needles, however, continued to clutter the orbit to this day. In 2007, China raised tensions by destroying one of its own weather satellites. The Russians and the Americans also tested such anti-satellite missile systems, but their targets were in lower orbits. Within a few months, the debris burned up in the atmosphere. The defunct Chinese satellite Fengyun 1C, however, was orbiting at an altitude of 850 kilometers. As a result, China's space weapon test scattered an estimated 40,000 fragments in orbit for a long time.
I don't understand why China decided to shoot down a satellite in such a high orbit. They must have known that the debris will remain in orbit for many, many years. In some sense, of course, the project was a show of force. They wanted to show other nations that they were capable of doing this. Unfortunately, however, it has had rather negative consequences for both military and civilian aerospace.
Then in the spring of 2019, India tested a satellite killer. The decommissioned Indian military satellite that they shot down was flying at an altitude of barely 300 kilometers. So most of the debris from the explosion burned up in the atmosphere relatively soon.
In recent decades, we've noticed that a few countries around the world apparently thought they also had to demonstrate their power in space by claiming they can play war even up there. I explicitly refer to it here as playing war and not waging war. I condemn it, of course. I have absolutely nothing good to say about it. For one thing, we already have enough problems here on Earth. Surely we don't need to fight one another in space as well. Moreover, they generate space debris, and we have enough of that. We should take the necessary steps to clean it up instead. The ESA does not participate in any of these military projects. The ESA Convention expressly states exclusively for peaceful purposes. And that's why we don't participate in such activities. And I also wish they would just cease.
After the USA, Russia, and China, India is now the fourth nation that can use rockets from the Earth to shoot down objects in space. Right from the beginning, with the advent of satellites, armed forces sought ways to destroy enemy objects in orbit. The U.S. Air Force, for example, also tested, among other things, anti-satellite missiles fired from aircraft, with success. But then the research program was canceled at the end of the 1980s. The USA has since focused on ship-based anti-satellite missile systems. But Russia has now resumed air-launched missile tests using MiG-31 combat jets that carry anti-satellite weapons up to the edge of the stratosphere.
Knowingly producing space debris simply by attempting to shoot down a satellite for military purposes, that's a little like polluting the environment. It can be tolerated up to a certain point, but eventually everyone suffers from it. And the same goes for space debris. Once you reach the point where you can no longer operate satellites, then of course you've gone too far.
Collateral damage from military anti-satellite weapons testing is a major annoyance, especially when a target is destroyed at a high altitude. The Chinese show of force created debris that will continue to orbit the Earth at high speed for almost 1,000 years.
Although we have plenty of debris out in space these days, we shouldn't forget that space is also pretty darn big. It can hold a whole lot of stuff. And that's the reason why the distance to a dangerous piece of space junk is currently about 400 kilometers. For the moment, the probability of a collision is still relatively low. But here's the long-term problem that we're going to have. Every tiny piece of debris can collide with another piece of debris, and that will create tens of thousands of new pieces of debris. And every piece of debris is just as dangerous on impact.
A collision of two objects can trigger something like a chain reaction, which theoretically accelerates and can no longer be stopped.
There's a risk that in certain Earth orbit regions, the quantity of debris eventually grows so high that you can't really conduct aerospace operations with reasonable means anymore, because you have to make too many evasive maneuvers just to keep your satellites safe. And that can really happen. It's called the Kessler syndrome. This could happen when space debris starts to collide with other space debris, creating new debris again and again with each subsequent collision. This then leads to a sort of chain reaction, where debris creates more debris through a continuous series of collisions.
This horror scenario was developed and mathematically modeled by the astronomer Donald J. Kessler. Sustained by this cascade effect, the unstoppable reproduction of debris could rapidly destroy all active near-Earth satellites. The conveniences of our digitalized world would come to an abrupt end.
Up to just a few years ago, there were far fewer active satellites. What we see today represents a significant change in the way the aerospace industry operates. There are many more small satellites today. Satellites you can purchase almost off the shelf, or whose components are commercially available and can be used to assemble satellites, almost like with a modular kit. That would only be a slight exaggeration. And that's why the number of active satellites in Earth's orbit is so much higher today than it was maybe 10 years ago.
The best way to reduce space debris is to bring the worn-out satellites back to Earth. And that's what they do anyway, sooner or later. It's only a matter of time. An object orbiting at an altitude of 160 kilometers falls back to Earth again within 24 hours. For satellites in a 36,000-kilometer high geostationary orbit, however, it takes longer, several million years. But they all come back eventually, without exception. There are re-entries every day as a result, and most objects burn up completely in the process. But some pieces of debris survive the ride through the atmosphere. Tanks made of stainless steel or titanium are the most common examples. The largest known piece of debris in space is the defunct environmental satellite ENVISAT.
ENVISAT is a relatively large satellite, a very complex instrument. a very complex satellite, about as large as a minibus. Yeah, roughly the size of a VW bus, in that range. Because it's so large, if NVSAT were to be hit by debris, the impact would produce a very, very large quantity of debris. So that means the risk potential in the event of an impact is higher than with a small satellite.
The defunct ESA satellite orbits the Earth at an altitude of a little over 760 kilometers. Since 2012, scientists have lost all control over this 8-ton boulder. Because NVSAT is traveling in an orbital region with a particularly high object density, it constitutes a serious danger.
NVSAT is a real problem because it will take a really long time for it to come back down. But nature is helping us out here because residual air up there creates drag that causes the satellite to come back down very, very slowly. Although it will take NVSAT 150 years, it will indeed come down eventually. All other satellites come down faster and then even burn up in the atmosphere. Not completely, unfortunately. In some cases, scraps remain that then fall to Earth. Do they represent a danger to us humans? No. If every human on the planet stood close together, we would just barely cover an area the size of Lake Constance. And it's certainly highly unlikely that a piece of debris would just happen to fall into Lake Constance. Nevertheless, that means we have to bring as many defunct satellites back down as possible. And one perfect example was the Mir space station. It was still controllable, and the Russians managed to make it fall into the Pacific Ocean.
The Russian space station Mir is the largest man-made structure ever removed from space. Launched in 1986, Mir reached the end of its service life in 2001. Mir was one of the greatest successes of the Soviet aerospace program. And prior to the establishment of the International Space Station, it was humanity's only continuously manned outpost in space. After the station was abandoned, the Russians could not simply leave the 124-ton uncontrolled structure in orbit.
The Mir space station occupied a very low Earth orbit at an altitude of about 400 kilometers. Such objects are also then brought back down to Earth. But that means we want their entry to be controlled, of course. So we reduce the object's orbital altitude, either by natural means or with rocket thrusters, till it reaches a sufficiently low Earth orbit. And then we fire rocket thrusters to actually cause the object to crash. And that means a controlled fall in a controlled corridor. With the Mir station, for example, this was carried out by a docked progress module, which then ultimately made the final burn, as they say, that brought the Mir station into a controlled re-entry.
With an object the size of Mir, uncontrolled re-entry would have been too great a risk. Under the direction of the Russian Space Agency, the complex recovery mission starts on March 23, 2001. With several precisely targeted thrust maneuvers of a docked Progress spacecraft, the station is pushed into a lower orbit and then deliberately forced to crash. Mir enters the Earth's atmosphere over the Pacific Ocean. The station breaks up. Its separate pieces burn up in the sky. Falling remnants of Mir are scattered across 1,500 kilometers of ocean, far from civilization. The mission is a success. A controlled crash is also the fate in store for the International Space Station. The final decision on its decommissioning has yet to be made, but in the end, most of the ISS will also burn up, and the rest will fall into the Pacific.
No doubt it's so large that some of it will beat the odds and make it all the way down. The whole thing won't burn up. It's the heaviest components that probably won't have that satisfaction. But the International Space Station has no radioactivity-based energy sources. So you might say there are no dangerous batteries on board. In that sense, what comes down then won't actually pose any danger anymore.
It remains to be determined whether a Russian or an American spacecraft will give the mortal blow that sends the International Space Station falling toward Earth. But its deorbiting scenarios are already under development.
To hit an intended crash site with pinpoint precision, that's really a high art that only very few people ever master. And that's why many satellite operators use another method. Simply bring it down and pray. Well, that works too. Meanwhile, there are more and more satellites in space, large and small. The small ones are not a big problem because most of them burn up. Only the large ones might become a problem. But the operators promise that in the future, they will systematically pull their satellites back down at the end of their service life. The question remains, can anyone put a satellite in space? The answer is yes, as long as that citizen's government says yes, because that government ultimately bears the liability for it.
The space surrounding the Earth has become a huge economic zone. The data from space are highly coveted and promise good profits. Highly complex technology can now be housed in tiny packages. Using that approach, more and more mini-satellite designs are being developed for specialized applications. The prices of these tiny satellites make going into space attractive, even for private companies.
We see that companies like Elon Musk's and also Amazon, among others, are thinking about constellations in order to have full coverage of the Earth. For example, for telecommunications or for Earth observation or navigation. These are very interesting approaches. But just now, when we're thinking about sending hundreds or thousands or tens of thousands of additional satellites into space, that's really when the issue of space debris becomes more important than ever, even more exciting and even more crucial, to develop technologies that also ensure the purposeful avoidance of space junk now, and not to just wait around happy as pie for the next 10,000 satellites.
There are strict rules in the satellite business, but not everyone follows them. When its application for approval to launch 4 test satellites was rejected, the U.S.-American startup Swarm Technologies just went ahead and launched them into space from India anyway. The FCC, the U.S. regulatory agency with authority over broadcasting, satellites, and cable, was not amused and slapped a $900,000 fine on the young entrepreneurs. Swarm Technologies has since obtained all necessary approvals and promises low-cost data exchange between devices on the ground via its SpaceB satellite network. Data from space also open up brand new opportunities in land management. Information applicable to soil analysis or irrigation, for example, or for the networking and control of agricultural machinery.
The downside of having many small satellites is that maybe one gets left behind or one of the little guys breaks down and then I produce space junk again. The trend is perfectly understandable, but so is the trend that in the end we also think about the waste and then dispose of it properly.
The future indeed belongs to constellations of small satellites. Space is open for private entrepreneurs. And more providers are supplying data from space for a continuous stream of new applications.
It's crucial that such constellations implement very highly reliable space debris prevention systems. Once they can guarantee that, then such constellations can also be operated safely in Earth orbit.
Networks of small and mini satellites fill important data gaps, and this is especially true in the field of climate and weather observation. They can be put to very specific uses and are nevertheless relatively inexpensive, rapidly equipped, and easy to operate. And because they orbit very close to the Earth, they're exposed to less cosmic radiation. Satellite clusters provide exhaustive data collection, and meteorologists are particularly reliant on continuous and verified measurements.
What can we do about this space junk problem? It's actually quite simple. We have to clear away these old, dead satellites, because when they're hit by a piece of debris, they fling apart into more debris. That's why the Americans have established an Orbital Debris Program Office. But it's just a paper tiger. It has no substance. The ESA is actually better. It has planned a concrete mission, the so-called Clear Space One. And with it, they want to bring an old rocket part of a Vega rocket back down from orbit.
With Clear Space One, a private company has been contracted for the first time to recover a piece of debris from space. The first active cleanup mission in space. It is a test that will remove from space an adapter piece weighing about 110 kilograms. And the mission is also conducting research on a possible future market. Satellite operators could be obliged to bring back their satellites themselves, or have a contracting company recover them for a fee.
Space agencies have discussed the topic of space junk among themselves time and again for many, many years now. Most of them say, we're monitoring, we're monitoring, we're monitoring. But monitoring still isn't disposal. And that's why, at the meeting with the ministers in 2019, I proposed to launch an actual mission now to genuinely reduce space debris.
There is no doubt that the ever-increasing number of satellites launched into space will cause serious problems in the future. And the most reasonable approach to solving that problem is to bring defunct satellites back to Earth.
If we could find a way to bring this space junk closer to the Earth, into the outer atmosphere, then the outer atmosphere, the drag, would slow it down anyway, and then sooner or later it would enter the atmosphere and burn up. That would be the most elegant solution.
Small rocket thruster modules could lower the orbit of defunct satellites. In lower orbits, a sail would also increase drag enough to cause the satellite to fall back to Earth faster. Or the space debris can be captured with a net and towed towards Earth. But the best option would be to equip all satellites with system-specific return mechanisms.
The approach is actually to try to achieve more sustainable aerospace operations. Basically, it's no different than for us here on Earth. When I avoid creating waste in the first place, or when I can use my systems longer, that's better than throwing things away and then having to clean up afterwards.
One successful example of extending the useful life of a satellite is the so-called MEV, the Mission Extension Vehicle. This probe is used to reactivate satellites that have run out of fuel but are otherwise still functional. In February 2020, this mini spacecraft successfully docked with the Intelsat 901 communications satellite and extended its life by 5 years.
What do we have to do to get this space junk problem under control? Well, we have to clear away all these dead satellites. This is technically feasible, but awfully expensive, because there are so many of them. And that's precisely why all space nations are holding back. But there's cause for hope, the Clear Space One mission of the ESA. What do we do with the many small pieces of debris? Well, there's nothing we can do about them. We can only wait until they come back down. And if we do nothing at all, we'll have a huge problem. Then the Kessler effect will overwhelm us. Then we'll have so much debris that we'll no longer be able to operate aerospace programs at all. Nobody wants that. So we have to act.
Satellites allow people the world over to communicate, transmit television signals, and maintain our networks worldwide. Earth orbit has long since developed into an economic market, and the available room around the Earth is gradually becoming scarce. More and more satellites in space are leaving more and more rubbish behind. Space junk. Year after year, this raises the risk of collisions involving satellites and their remnants. We are putting our aerospace programs themselves in danger, and along with it, our modern life in the digitalized world.